Good morning, everyone. We're the FPGA versus microcontroller team, sponsored by Lattice FPGAvMicro. My name is Mal Lopez.
I'm Alexandra Morocco.
I'm Andy Brown.
And I'm Rumer Kalachin.
For our project, Lattice asked us to evaluate the difference between an FPGA and an ARM-based microcontroller while running a well-known speech recognition algorithm called Pocket Sphinx. Our objective was to evaluate each platform's suitability for executing speech recognition with respect to power dissipation and runtime performance.
To address our problem statement, we derived a research project that would compare an FPGA and a microcontroller as they're running the same portion of our speech recognition algorithm. To achieve this, we chose two comparable devices. We ported the same portion of the speech recognition algorithm to each board. We then collected and analyzed power and performance measurements as they're running each portion.
Our approach is to find a speech recognition algorithm that we can implement on each board. We decided on CMU's speech recognition engine called Pocket Sphinx for its specificity in embedded devices, its open source library, and its highly supported community.
After choosing an algorithm, we needed to choose a profiler that could best characterize the entire Pocket Sphinx continuous program. By understanding the full functionality of this program, we could then find a section of it that we could implement in hardware description language, upload to our FPGA, and compare its performance to the C implementation uploaded to our microcontroller.
For our devices, we chose the Lattice ECP3 Versa for our FPGA, and for our microcontroller, we chose the STM32F4 Discovery board for its low and ARM M4 processor.
After software and hardware implementation, we'll be measuring the power and time of each device. For the CPU, we'll be using a kilowatt device. For the microcontroller, we'll be measuring the current drawn over time with the voltage supplied to it. While the FPGA will be using the Lattice Diamond software power calculator with our simulation. So, as soon as the Pocket Sphinx receives an audio file, it then listens for distinct sounds spoken and splits it based on utterances such as beating noises, pauses, and so on, and then tries to recognize what is being said. Pocket Sphinx then extracts an hypothesis based on the acoustic model, the language model, and gram language model, phonetic dictionary, mathematic calculations based on probabilities on each model to help hypothesize the correct word.
Profiling with the continuous program was done with Intel's analysis tool VTune Amplifier XE. With VTune, we were able to produce a visual map of the entire program, including all functions and subfunctions visited, as well as the total CPU processing that was spent at each function. Thorough analysis of our visual map demonstrated that CMU had programmed and organized their algorithm to be very well balanced, although we found our largest hotspot to be at a function called findBG.
For an audio file consisting of 26 words over 9 seconds, findBG was called over 5 million times. FindBG is a bottom-level function that performs a binary and linear search on a static bigram array. A bigram is a sequence of two elements, typically two letters, words, or syllables, that appear right next to each other. If you look at the diagram, we have a syllable breakdown of the word tomato and its pronunciations, tomato versus tomato. Two nodes represent one bigram, and the connecting line represents the bigram probability, which findBG helps to determine.
For our microcontroller implementation, we sought to simulate our chosen function, findBG, on the M4 processor as if it were processing our chosen WAV file, however in a standalone manner. To do this, we isolated the input data set and stored it on an SD card. Our microimplementation then read from the SD card and passed the input data set to an identical implementation of the source code of findBG, one data set at a time. We then collected power performance measurements in various iterations.
Our design approach for the FPGA implementation involved creating a state machine for the findBG algorithm. We also needed 2 additional state machines to control access to the memory instantiations we created out of embedded block RAM on These memory instantiations included static input data, as well as the word ID array that FindBG accessed. In conjunction with the microcontroller, we performed the same timing and power measurements on the FPGA.
Our hardware design components consists of 3 elements. First, we take a new input from the embedded block RAM, and then we feed it into FindBG and allow it to do its computation while simultaneously updating the word ID from its corresponding memory bank. And we let this loop go on until we can finally return the bigram probability at the end.
So as we can see here, the time taken for the microcontroller for each iteration of 5,000, 10,000, 20,000 more than the FPGAs, while the power consumed by the microcontroller at each iteration of 5,000, 10,000, 20,000 power is consumed more by the microcontroller than the FPGA. So we can conclude that the Lattice ECP3 is more efficient in power and performance than the microcontroller.
For the next steps in our project, because our simulations because our data was based on simulation, our next step is to measure power on the FPGA during a live run.
Additionally, we plan to implement both of our designs for the live interaction of instruments, as well as consider additional hotspot functions to accelerate.
This concludes our presentation. If you have any more questions, please follow up with us.
Thank you.